Okay, let's get started on chapter 5. And we're going to combine our descriptive statistics, is what we did in chapters 2 and 3, and probability that we did in chapter 4. And so what we're doing is we're going to analyze probability distributions. So in other words, we are going to describe what will probably happen. So there's a reason why we talked about probability briefly before we got to this chapter. So what we're going to do is we're going to deal with random variables, and there's two kinds. There's a discrete that we're going to talk about in chapter 5, and then there's a continuous random variable that we're going to talk about in chapter 6. Now what happens with discrete random variables is that we really have a certain number of outcomes that we can expect. So for instance, we're going to roll a single die, and we know the outcome will be 1, 2, 3, 4, 5, or 6. You're not going to get a 2.5 when you roll a die. And you know you can do it this way. You can collect your sample like we did in chapters 2 and 3, and you can come up with the mean and the standard deviation using the frequency table, or you can calculate the probability as we did in chapter 4. And so what we're doing in chapter 5 is we're putting these together to get a theoretical model on how we would describe our experiment. So we expect each value, each face of the die to come up 1/6 of the time. I'm going to show you how we're going to use StatCrunch to calculate the mean and the standard deviation. Now there is a formula that's similar to the standard deviation with the frequency table, but guess what? We're going to use StatCrunch, so don't panic. So what's a random variable? A random variable is a variable that describes the numerical, and this is important, numerical outcome of a random phenomenon. Most of the time we talk about them with capital letters from the end of the alphabet. And so what we talk about, a normal random variable, is going to be talked about with a capital N, meaning it's normal, and then in parentheses the first number will be the mean and the second number will be the standard deviation. And we use the symbols for the parameters because we are assuming this about the population, not the sample. And then the probability distribution tells us what values that variable can take and how often that they will take that. Now, when we can count the possibilities, we are talking about discrete random variables, and these are the ones that we're going to deal with in our chapter today. Now, discrete random variables would be rolling dice and counting the pips on the faces. It's going to be picking cards if we look at the value of the card. It will be the number of pets owned and or the numerical day of the month. How many days of class a student has missed. One thing about the random variable is our variable needs to be quantitative. It cannot be qualitative. We use a different kind of probability table when we are doing qualitative studies. The second type of random variable is a continuous variable. That means that the variable can take on any value in the interval. And then our probability is the area under the density curve. This is what we're going to talk about in chapter 6. So examples of continuous random variables would be height, ACT scores, IQ scores, weight, temperature, the time it takes to travel to work. So there's a continuous value. We can look at these using probability histograms, And again, it's very similar to a relative frequency histogram, but now our vertical scales show the probability. So as you can see, for this data that was collected here, we are looking at the probability of the number of Mexican American jurors among 12. So now, how do we talk about our probability distributions? Just like in chapter 4, we know the probability of all the possible outcomes need to add up to 1. We know the probability of a single outcome has to be inclusive between 0 and 1. When the probability is 0, it isn't going to happen. When the probability is 1, it will happen. The mean is the sum of each value of our variable times its probability. And we'll look at that in just a second. And then our variation, we have two formulas for the variation. One is definitional, one is computational. But again, don't panic because we're going to use StatCrunch. Our standard deviation is going to be the square root of our variation. Now in StatCrunch, you're going to go to Stat, then you're going to go to Calculators, and then you're going to go to Custom. And I will show you how to do that in just a bit. Okay, let's do an example here so that we look at how we do the mean and the standard deviation on StatCrunch. We have this data that is the number of cars that failed among 6 3-year-old Ford Focuses, and our number is the number that failed among the 6 that were tested for roadworthiness. And you can see the data here. I've already checked to see that it is a probability distribution. First of all, it is, because my x variable are numbers, and then the probability adds up to 0.998, which is pretty darn close. That's because of rounding. So we can say the sum of the probabilities is about 1. Now this 1 plus means it's a little bit more than 0, but it's extremely small. So what I've done is I've put this data into StatCrunch. So here's the data in StatCrunch, and you can see that I just entered it. Remember, when you go to StatCrunch, you want to go to the website. You want to use that bottom link in My Data to copy or paste or type into a empty data table, and that's what I did. So I'm going to go to Stat. I think I go to Stat and Calculators. I go down here to Custom. My values are in my X column, and my weights are in my probability column, the P of X. And then I'm going to compute. Okay, and right there it tells me that the mean is 0.89579,158, and the probability that the standard deviation is 0.867. I'm going to go to Stat Calculators, down to Custom, and you put your values for X in the values column, and the weights are the probabilities. And then I simply do compute, and that's where I'm going to find my mean and my standard deviation. Now, the answer that I have in the textbook, they rounded both to 0.9. So we take one place value beyond our variables. So we take it to 1 decimal place, since these are all whole numbers. Okay, so again, a reminder for the round off rule for the mean, the standard deviation, the variation. We're going to go one more decimal place than our data values. So if our x's are integers as they were in the last example, we're going to round our mean and our standard deviation to 1 decimal place. Now, just like we did in the past chapters, our usual results are between plus and minus 2 standard deviation units from the mean. So an unusual results are outside these limits. Let's look at an example. Okay, now let's look at number 20, where we look at the range rule of thumb for unusual events. So remember, the range rule of thumb is the mean plus or minus 2 standard deviation units. And so our mean of our probability distribution for car failures was 0.9 plus 2 times our standard deviation, which was 0.9, which is going to be 0.9 plus 1.8, which comes out to be 2.7. And then that's our high unusual value, and then our low unusual value would be 0.9 minus 2 times 0.9, which comes out to be a negative number, which doesn't make sense with our data set, because 0 is the lowest we can have. So our range rule of thumb will be that we can't have fewer than no cars fail, and if we have more than 2.7 cars, 3 cars would be unusual. So that's how we would work on that. So it says, is 3 an unusually high number of failures among 6 cars tested? Yes, it is, because it's beyond our high end of our unusual usual values. So 3 is an unusual number. Event rule. When we are under our given assumptions, for instance in the car, that we're dealing with 6 cars, and we gather data on in many samples how many cars of how many 3-year-old Ford Focus would fail, and we have that data that was in the table. So when we have a rare event, it means the probability that that outcome happening is extremely small. When we get something that is outside of our 2 standard deviation units above and below the mean, that means that the event is rare enough that the assumption that we are making is probably not correct. So for a fair coin, we're going to assume that the probability of heads is 0.5. You get heads half the time, you get tails half the time. If we would make 1,000 tosses and we got 992 heads and 1,000 tosses, that is not going to happen very often if the coin is truly fair. So if we got data like that, that means it's a rare event. So we have just gathered evidence against the assumption that our coin is fair, and so we probably should throw that out. So we have evidence against the statement the coin is fair, so we can say the coin is probably not fair. Now in statistics we always use fuzzy language because, again, we can't prove anything is true, we can only show that it's probably false. And so statisticians use language like, it appears that, this study gives strong evidence that. We don't ever say this study proves that, because that is too definite. And because we're dealing with probability, we need to make sure that we use imprecise language. So again, unusual results are the probability that it's that value or more is less than 0.05. Unusually low, the probability that it's a certain value or less is less than 0.05. So this 0.05 is usually the probability that we cut off between usual and unusual. So if we think about that standard normal curve, we're looking out in the tails, and we'll talk more about that in chapter 6.
Okay, so now let's move on to 21 using our same data set, and let's find the probability of getting exactly 3 cars that fail among the 6 tested. Well, you could do that one and just read it off the table. 3 cars, the probability of exactly 3 cars is 0.041. But you can also do it using your calculator that you used before. I'm simply going to change my sign to be equal, and I'm going to change my number to be 3, and I'm going to click compute, and there I get my answer, 0.041, and that comes from the problem that I just looked at. So now let's find the probability of getting 3 or more cars. Okay, 3 is an acceptable answer. So what I'm going to do is, if we would do it by hand, we take 3 and we would sum all those values that are 3 and above. You can do it on your calculator, changing that to greater than or equal to, and you see we get 0.04609 218, and if we added those together, that's what we would get. So again, we would take that out 1 decimal place, so it'd be 0.05. Then let's look at, see which probability is relevant for determining whether 3 is an unusually high number of failures among the 6 cars tested. That's going to be greater than or equal to 3. If we look at 3, that would round to 0.04. If we look at 4, that's going to round to 0.05. So 4 cars is going to be unusual using this. Is 3 an unusually high number of failures? Well, yes, it was, because remember when we used the range rule of thumb, we were going to get 2.7 failures in groups of 6, and so this is an unusually high number of failures. The probability of 3 or more failures is 0.046, which is very low. It's less than 0.05, so it is unusual. Let's continue on to number 22. Find the probability of getting exactly 1 car that fails in among the 6 cars tested. Well, right here we can do that. We're going to go to our calculator. We're going to do equal to 1. And you can see that that's going to happen about 40% of the time. If we go back to the questions, find the probability of getting 1 or few cars that fail. Let me say that again. Find the probability of getting 1 or fewer cars that fail among the 6 cars tested. Then I'm going to go to my calculator. 1 or fewer would be less than or equal to 1, and that's going to happen almost 78% of the time. And which probability is relevant for determining whether 1 is an unusually low number of cars that fail during the 6 cars tested, A or B? It's going to be B, because no cars failing happens, and it happens quite a lot. And then, is 1 an unusually low number of cars that fail among the 6 cars tested? Why or why not? No, it's not unusual, because the probability is almost 78%, which is not very low. And remember, very low is less than or equal to 0.05.
About expected value. Now what's going to happen when you want to know what is the expected value of a series of outcomes? Then you're going to use this formula. You're going to take each possible outcome, You're going to multiply it by its probability, and then you're going to add those up. That'll be your expected outcome. I hope that sounds familiar, because that's the exact same formula for the mean. And so expected value is simply the mean value. Let's go to an example from your textbook about the expected value.
Okay, let's look at an expected value problem, and let's take a minute and look at number 26 at the end of the section, and in my book it's on page 233. And it says the television game show Deal or No Deal begins with an individual suitcases containing the amounts of 1 cent, $1, $5, $10, $25, $50, $75, so on and so forth, up to $1 million. If a player adopts a strategy of choosing the option of no deal until one suitcase remains, the payoff is one of the amounts listed, and they're all equally likely. Okay, so what we need to do is we need to come up with a probability. So let's list our values. And they say they're all equally likely. So each of these are equally likely, so they will happen 1/26th of the time. So let's say that our probability for each one is 0.3846. So that's our probability all the way down. And if I take that times 26, that's going to give me a sum of 0.999, so on and so forth. So that's pretty darn close to 1, so I know this is a probability distribution. So what it says is I want to find the expected value for this strategy, and I want to find the value of the standard deviation. We want to use the range rule of thumb to identify the range of unusual outcomes based on the preceding results. Is the results of 750,000 or a million unusually high? Why or why not? Okay, first of all, let's go ahead and remember what the expected value is the mean. So the expected value is exactly the same as the mean of a probability distribution. So the expected value is the sum of each value times its probability, which is the same as the mean. So what are we going to do? Well, I think the easiest way to do this is go back to StatCrunch. So let's do that. So as I do all this, I get my distribution, and I get that the mean of the distribution, which is the expected value, comes out to be $131,477.54. Now the next question says, find the value of the standard deviation. Well, that's on my calculator that I did in StatCrunch. So my standard deviation is going to be $253,584.47. So now it says use the range rule of thumb to identify unusual values. So remember that usual values are the mean plus or minus 2 standard deviation units. So that means our maximum usual value is going to be $131,477.54 plus 2 times our standard deviation, and it's going to be that value minus 2 standard deviation units. So when we add it, we get $638,646.48. When we subtract it, we get a negative $375,691.40, which they're not going to make you pay them. So this is the same as 0. And so the last part of the question says, based on the preceding results, is a result of $750,000 or $1 million unusually high? Well, our highest usual value is $638,000. So both $750,000 and $1 million are beyond our usual values. So, and 3 little dots like this means therefore they are unusual. So remember, expected value is the same as the mean, and you can do that on StatCrunch using the calculator.